Hi, everyone. I'm the first Ryan McKinven. I'm a postdoc here at McGill. We're not here at McGill, but at McGill. So yeah, you're in for a very content-heavy session, I think. It'll be very interesting. So this is a session dedicated to FRB localizers. And to start us off is Shannon, second Ryan, who will be telling us about ASKAP.
Yeah, I'll put the microphone up there. So yeah, I'd also like to acknowledge the Wadri Yamaji people as the traditional owners of the ASKAP site. It's a real great pleasure to be on their land. It's a very quiet land, which allows us to interference that all of us face when we're doing our radio observations. So the telescope is in the background there. So we've got 36 12-meter antennas. We have unique phased array feed receivers. So we form 36 beams on the sky digitally, and this allows us to cover a 30 square degree field of view. Give you a sense for our experiments. CRAFT is the acronym there. And the idea here, motivation here is to do FRB searches commensurately with all other observing that's done on the telescope. So really we're trying to sit in the background and grab data from wherever we can in the data pipeline and search for dispersed pulses. The method that we currently use to search is what we call the incoherent sum. So we take the data itself is in observations roughly between 800 and 1.6 gigahertz central frequency. That depends on what project's operating. We get the data from individual antenna-based beamformers, and the data has roughly a millisecond time resolution and a megahertz frequency resolution. So this is going to impact our sensitivity to most dispersed pulses. The samples are detected and integrated, and then added together in intensity. So this is why we call it an incoherent sum. And we search for the dispersed signals with FREDA on a single GPU on site. As I said, these searches have been operating commensally or in filler mode. And what I mean by that is that in between other scheduled observations, there's some flexibility to run the CRAFT system on other fields. So that's how we find FRBs. Of course, with in those intensities, you can't localize them that well. So to do that, what we do is we have voltage buffers. Given the amount of RAM that's available on the system and the number of beams that we have, we don't have long buffers. We only have 3 seconds. So we have to be able to find the FRB and download the buffer very quickly. We get a signal to noise ratio boost because now we can go and image those. We image the voltages. And also we get an increase because of the time and frequency resolution we can tailor. We're not subject to 1 megahertz in 1 millisecond. So you can see how our signal to noise ratio can increase as we go up. So this allows us to get positions and high time resolution spectral polarimetry in post-processing. So once we have our FRB positions, we want to go and find out where they're coming from. So we have to bootstrap from the FRB image itself to Gaia, but when we do so, we can get positions as accurate as 100 milliarc seconds. With those positions, now we follow up. We've been using the VLT, Keck, and Gemini to find FRB hosts and get the redshifts. We have a large ESO project to do FRB host galaxy follow-up that's ongoing, where we use a number of the ESO instruments to get fully the most detail about what the host galaxies are like. X mentioned earlier, we do IFU, integral field unit spectroscopy as well, to understand the host galaxies and the foreground. So we've been using MUSE, KCWI, and AO Omega. We've been looking for persistent radio sources and evidence for star formation in host galaxies using ATCA, VLA, and MeerTRAP. There aren't any persistent radio sources, but there is some evidence for star formation in some of these galaxies. We use Parks, GBT, and FAST to search for repetitions. If you've been to an FRB conference, we always talk about do they all repeat or not. we've only seen the one FRB repeat in any of the FRBs that we found. And of course, when we want to get to 100 millisecond spatial resolution, you use Hubble Lama. So here are the FRBs. There's around 26 localized and 24 host galaxies, 2 with no host identified. This is actually a plot from Sunil showing the most recent McQuart relation using craft FRBs and a handful of other ones localized by other instruments. The DMs are 200 to 1800, and the DM 1800 one is yet to be head of a host galaxy. When we look at the host galaxies, this is what they look like. A lot of them have spiral arms. A lot of them have evidence for star formation, and you can see here as you go out to redshift 1, things start to look more crazy. But if you go you start looking at more distant universe, things just tend to look crazy. And you can see that the circles show that instead of ellipses. So as we discussed earlier, most of these galaxies are star forming, and most are close to the star forming main sequence based on work that Alexa led, which did a better improved treatment of comparison of field galaxies and the FRB host galaxies. We know many originate on or near spiral arms, and this rules out, I think this rules out these FRBs coming from globular clusters, because that wouldn't happen by chance. Most of these galaxies are much less luminous than the Milky Way. So when we talk about trying to follow up things at high redshift, it's going to make things even harder. And X touched on this earlier, that how do we deal with the FRB host galaxies that we don't find because we can't go deep enough, and how does that by cosmological experiments? And we need to think about that. And just an example of a commensal FRB detection. This was detected commensal with Wallaby, which is the H1 survey. And what we're seeing here is the little red circle is the FRB position, which is coming from quite close to the center of the face-on galaxy. You can see the lovely spiral arms and the optical, and the contours are showing you the H1. So there's a nice here to get all that information just from one observation. We can look at these FRBs at high time resolution, and we see a variety of morphology, stuff that look like the quote-unquote sand trap bones. This one we know repeats. This one has sad trombonish spectra, but we haven't seen repetitions from it. And then things that look markedly different. So there's a variety of pulse morphologies, and really, the steps here is trying to connect these to the hosts and locations with the hosts. The moment we're finalizing rotation measures and the spectral depolarization of the FRBs, understanding the scattering, and searching for the coherence of the emission. So what I'm trying to discuss here is just ways that we can use populations of host galaxies, populations of FRBs, and combine them together to understand, bring the most detailed description of what FRBs are. So going from the populations to individual sources, this is a discovery from last year where we had a dispersion measure of 1450, a rotation measure of 220. That's in our frame. So it's given the redshift, it goes up to 880 in the host frame. And monoscattering, we're not quite sure where it's coming from. If this is all these things are at the same redshift, so we're not sure if this is one galaxy that's been sort of disturbed, or if there's a little group here or stuff like that. But really, the importance here is that it revises FRB energetics. ASKAP as a telescope is not the most sensitive, so really this thing gives a promise for able to detect things at high redshift. So I'll skip over this. This is the FRB, a previous FRB that we found that has a similarly high dispersion measure, but no host. And we've struggled with trying to figure out what's going on here. We ask, say we need to go to space because we need the sensitivity, and they say go deeper from the ground, and then we ask for IFU to see, look what's there, because FRBs don't necessarily have to come from right where the center of the emission is, and they say use HST. So Craco is the next step. This is the fast coherent backend. It's FPGAs. It's searching FRBs in 23 terapixels per second. That's 800,000 people streaming YouTube at once. this provides us a great increased sensitivity with respect to ASKAP, the ICS system, a factor of 10 greater, potentially a factor of 10 greater detection rate in FRB every 2 days. We'll have arc-second positions publicly available immediately, and we'll be sensitive for transients from 1 millisecond to 10 milliseconds. Here's what it looks like on the FPGA card, where all the math is happening, all the number crunching is happening. You know, it's a very complicated thing to set up. We are able to now detect. We're online and have first light from the system. We're able to detect pulses from bright pulsars. You know, look them and detect all the bright pulsars from the pulsars. Our raw pipeline is running offline at 860 microseconds, so we're getting close there and finding the pulsars at the correct dispersion measures. So what we've learned and why I'm excited is, of course, that we are seeing FRBs come from cosmological distances. We're able to probe the CGM, and there's forays into cosmology that are ongoing, and there's really an opportunity to find a population of FRBs at high redshifts. On top of that, there's basically one other point is that just multidisciplinary collaborations are recipes for success. We've benefited from having engineers, theorists, people who study light and waves and light and photons. It's been really valuable. And finally, it's been a really good field for, I think, empowering and developing leadership for our students and ECRs. So with that, I'll take questions. Thank you.
Great, thank you, Ryan. Any questions in the room?
Yeah, you mentioned that the Redshift 1 localization revises FRB energetics. What do you mean more specifically? You mean that it pushes up your thinking about what the highest possible energy FRBs are? And what is that quantitatively? How much did it change by?
Yeah, it changed it by like a factor of 2 or 4, but really the issue is that when people, common models assume that there's like a Schechter function, which is basically saying there's an exponential cutoff in energies. So if you find anything sort of more luminous than your model is predicting, that's why it pushes things out. I put a question out there to the community as to if we need to have these exponential cutoffs, is it physically do we expect there to be that energy cutoff at our current sensitive, our current constraints, or if there really is potential to have even more energetic FRBs?
Okay, thank you.
You mentioned there are 2 or a couple FRBs that are hostess. I was wondering if they just have like really extreme offset, or the galaxies are just too faint to be detected.
Yeah, it's not. It's most likely the galaxies are too faint to be detected in in imaging. With our current observations, so this is sort of where we're thinking this one might be, but. So the 2 approaches would be either to go and use an integral field unit spectrograph and look for line emission close to, but not on the FRB position, or go deeper, with either space or even deeper up in the ground.
Time for one quick question.
So you mentioned Krakow has had first light.
Yeah.
Any predictions on when first FRB?
Yeah, I guess I'd be hopeful that we'd be, sort of finding FRBs this year. That would be, the thing is, so like basically that we are able to now run the system and starting to do scientific commissioning with the system, basically commensal to ASKAP surveys. So that will allow us to sort of really, get to the, get up and running quicker.
Okay, we can thank Ryan again. Our next speaker is Franz Kirsten from Chalmers, who will be telling us about Precise. And he will be joining remotely, I believe.
Okay. I take it that works. Right, so thanks a lot for having me. It's super exciting to be presenting our PRECISE project and our latest results at this very, very nice workshop. So yeah, I'll just take a little bit through PRECISE, where we started and where we are right now. And this is, of course, all on a rather large, loose collaboration called PRECISE. And a lot of what I'm presenting here is also partially funded through AstroFlash. So let's just go straight into it and start with what PRECISE is actually meant to stand for. So at the time when we started, it was all about pinpointing, repeating CHIME sources with EVN dishes, and the best acronym to actually capture this was obviously PRECISE. This started off with the first CHIME repeaters. So this is just the tables, first two tables of the published repeaters, and what you can see here is obviously that those repeaters, they were all very high in declination, so 50 and above, most of them. And secondly, they were silly bright, so several Jansky milliseconds. So compolar high in declination, of course, means it's a compolar for the EVN dishes, and bright means that you don't necessarily need a big dish to detect them, because something like a 25, 30 meter dish, your detection threshold is somewhere around 5-6 Jansky milliseconds. The latest addition to the CHIME repeaters, the trend continues there. We still have fairly high declination sources, and they're still bright. So nothing much has changed. There's a few that are not that high, but that doesn't matter. So since all you really need is a lot of time on sky to detect those repeaters, and many of the EVN dishes, which are those 25 to 30 meter class dishes, they're mostly just observing during EVN sessions, and they have a lot of time on their hands outside of this. We just thought, okay, they're bright. We have a lot of time, they're circumpolar. And so we contacted all the different EVN directors and just said, look, we have this idea. Can we schedule observations and monitor the repeaters? Because this is how we started. We were sort of shadowing CHIME observations, shadowing those repeaters that were going through the CHIME beam at the time, using CHIME as our triggering stations, hoping that when CHIME saw a burst, then we would see one too, to then localize it with the smaller dishes. It didn't take long for us to then figure out that, it's not really broadband emission. When you see it in the CHIME band, you don't necessarily see it at L band, which is what we observe, so around 1.4 gigahertz. So this has evolved. Since February 2022, we also have eMerlin as part of our array. So that doesn't just improve the UV coverage, so improving our point spread function, but of course it also increases our sensitivity to extended emission. So we can, to some degree, say if there is a persistent radius source associated with an FRB, we can say, okay, it is extended on those scales or it's not. Which is, of course, extremely nice to then look for star formation or similar. Like I said, just the monitoring and using CHIME as our detector wasn't going to work so well on the long term. So starting January 2020, so we started in 2019, and 3 months later, we started to have Effelsberg in this array. Later on also the SRC, so the 65 meter edition in Sardinia. And we still have this setup that we always have Effelsberg in the array, which is our detecting station. At the station, we record with the VLBI backend. So this means we have the raw voltages that we record, and we get about 10 hours per week on the dish, on the Effelsberg dish, 100 meter station. And at SRT, we do a similar thing. We used to get about 6 hours per week. Currently, the dish is offline, but once SRT comes back online, we'll use the SRT as our detection station, and then we sort of sometimes use we can expand our time on source, whether we use Effelsberg or SRT as the detecting instrument. The whole processing happens on a cluster or here in Sweden. It's a moderate machine, 20 CPUs, 1 GPU, and we just convert those baseband data to filter banks. And we then search the data with Heimdall, classify with fetch. And typically we search our data at 64 to 128 microseconds, depending on the DM, because everything is done. We dedisperse incoherently, so there is a limit to the time resolution we can search it. And typically it takes about 24 hours between the end of an observation and us knowing whether or not we had a burst. In case of a burst, we then trigger a correlation-only proposal that we had in place until recently. So this is most of our data is just noise. Most of it is just thrown away within a week. But if there is a burst, we trigger, and then all the data are being correlated at CHIME. So between 2019 and 2022, we had about 25 triggers on 8 different FRBs. At this point now, Precise has become an EVN light background project since 1st of February. So we're not running this ad hoc array anymore. We are now sort of an official EVN project, which grants us 750 hours per year. We have access to the full array. We don't need to ask for letters of support anymore. And it still works. And so it's light in the sense that not all of our data are correlated. We have up to 12 triggers per year. So we can correlate 12 of our observing runs, which depends a bit on the year, can prove tight or not. Some years we get more bursts than others. At Effelsberg, and also for the eMerlins, we still need to propose separately. So this is a bit of the time we spend on Sky for the different dishes in the different years. Takeaway sort of that we do observe about 500 hours per year. Some dishes more than others, but on average, we have some 6 or 7 stations in the array. Because not everybody, so this is still working on a best effort basis, but 500 hours per year, I think is quite good. These are just a bunch of the sources. We have some favorites and some that we do not observe that often, but this is sort of currently the catalog of sources that we cycle through. We typically decide which source to observe depending on its activity. We use CHIME as one of the CHIME VOE events, and also notifications about repetitions to sort of decide which one we're going to observe. And that's proven quite successful. So this is, so what has come out of this? This is one of those results which was discussed already. So that's the FRB and the M81 globular cluster, closest FRB, and it's of course these sort of localizations are only possible with the longest baselines, because we can actually say here that this FRB is actually offset from the center of light in this globular cluster, which is of course interesting because it's not in the closest region where all of the tight binaries happen. It's somewhat offset. So, there's a lot of discussion going on what's happening there. Here, that's another interesting point of the longest baselines. This is FRB 2020-11-24A, also one of the very active repeaters, where in the first localizations, which are here with the different colors in green, magenta, pink, whatever, where the localization regions that all sort of overlapped, and there was claim of persistent emission, but then thanks to the long baselines, we could show here on the left, this is the dirty map of the localization, and then on the right in the color, that's the deep map. So this is, I think, 4 or 5 hours of integration on source, that there is no persistent radio emission, and overlaid is the 22 gigahertz contours where you do see extended emission. So obviously there's some star formation happening, but no persistent radio source. What is coming up? We have a bunch of localizations that are in prep. So here, this is 2019-02-08A. We have, I think this is just one burst with an OK array, and typically we have 1 or 2 baselines that dominate the visibilities, and then you can sort of fit the cross section of these dominating baselines to sort of fit a Gaussian to the localization region. For this particular source, we have not yet seen much in the optical. So the question is that a super faint dwarf galaxy, or is it potentially a globular cluster in the outskirts of one of these hosts? So this is all still work in progress, and will come out sometime either still later this year or next year. Let's see. Then we are also we're following up also on 2012-1102A, so the first repeater R1. This is work done by Mark Snelders, also in Jason's group at University of Amsterdam. Here we have two bursts in two different epochs. The color on the left here, this is the 7 bursts stacked. It's a dirty map, and as you can see, we have a nice localization here. On top of that, you have the contours. So this is the clean contours of the persistent radio source. Essentially, we're confirming here the results that Benito published in 2017. We're still working on improving that whole localization to try and improve the uncertainty on this offset down to 1 parsec. Currently, from Benito's work, was 40 parsec, and we're trying to improve that to become less than 1 parsec. This is also work in progress. Then we have we detected a burst from 2019 0520B, which is the so-called R1 twin. So the dirty map here on the left is horrible, but this is because this is only a 4-station array. During the 2 or 3 of the antennas that were supposed to observe did not observe in the end, and so we have a burst, but only 4 antennas. So the localization of the burst itself is very crude. But we had several hours on source, and we do see that the persistent radio source also on the VLBI scales. And this is work done by Shivani Bandari, and it's also will come out soonish. Now, the interesting thing with this source here, so this is the FRB 2019-02-08A. This was extremely active earlier this year, and we, in 2 epochs, we detected 49 and 117 bursts respectively. And what you see here on the left, I hope this GIF comes through and is actually coming through as an animation. You can see how Earth rotates, because the bursts appeared all throughout the entire observation, and you see this cross pattern rotating while Earth rotates, obviously. And then on the right, this is just incrementally stacking the individual bursts that then obviously helps you to get a nice localization. With that localization, this is what we have here on the left. So this pink cross is what we measure. The black ellipse is the error ellipse from DSA 110. We're slightly outside this region, so somewhat closer to the center of the galaxy. There is one little annoying issue still ongoing, because we do have, despite the fact that we have, almost 170 bursts, we do have a 50 millisecond offset between the 2 different epochs. So it just points out that even if you have a ridiculous amount of bursts, you still need to take care of the systematics that Daniela mentioned in the beginning. And this is also work done by Dante, so he's got to do all the fun work here. That already brings me to the end here, that PRECISE is great to pinpoint FRBs with millisecond resolution, and of course to also see if there's persistent source. We're always doing the optical follow-up, obviously, to then check the local environment. Even in the future, for nearby FRBs, the millisecond localization will be crucial, because something like ELT will have VLBI-like astrometry to then really probe the local environment. So with this, we've more than tripled the number of FRBs with millisecond localization, but just like Daniela said, we're never going to have a huge sample of millisecond localizations. But those that we have, they're hopefully going to give us a clue on the long term. And next up, Jason, I got this nice ERC grant, which will then help us to expand on PRECISE, so such a high time resolution, observe more And this is also something that will help us to actually expand on our single dish observation, something I did not go into too much detail, but this is using the smaller EVN dishes to actually spend thousands of hours on individual sources. But that's a different talk, and I'll take questions from you. Thank you.
Thank you, Franz. We have time for maybe one quick question. No questions? Nothing on Zoom? Okay, I think Matthias here.
I was just wondering what the longest baseline that you guys have with EVN is that you use.
That would be one of the baselines to China. So this is Europe to China. What is that? Some 4,000, 5,000 kilometers? I'm probably exaggerating here. From the top of my head, no, that's 2,000 or 3,000, right? Some of that.
Okay. Well, thank you, Franz. We can thank the speaker again.
Thanks.
And now Liam Connor, who will be telling us about the DSA 110.
Should I be changing slides with this? Okay, great. Yeah, so I'm going to give an update and an overview of the DSA 110. So first, let me introduce the interferometer, describe the FRB search that we're running on it, and then I'll step through some of the early science results that we've had in sort of the past 6 months or so. I'm giving this talk on behalf of the DSA 110 team. Here's sort of the group on campus at Caltech in Pasadena. The thing was largely built by the staff at OVRO. So here's the Caltech OVRO staff, the Owens Valley Radio Observatory, which is about 4 hours north of Pasadena. So here's an overview of the site. The yellow T, that's the DSA 110's core, where we're actually searching for FRBs 24/7. If we see something, then we trigger the outrigger antennas, which you see that they kind of trace the perimeter of the observatory. Those are the little blue markers there. And they're operating in time machine mode. If we see something, they save voltage data, and we can do offline interferometric localization. So I always point out that, of all the amazing telescopes around the world that have done FRB science the past decade, the main thing they have in common is that they were not built for FRB science, right? Westerbork existed long before the Aperitif Arts Search was proposed, CHIME, same thing, Parks, ASKAP, and so on. This is kind of the one exception to that rule. DSA 110 was specifically built to find and localize fast radio bursts. At the moment, since we're operating in a commissioning mode, we've only populated the east-west arm, which you can see there. So we have 48 antennas in the core right now in the east-west arm, and it's on those that we're searching in real time for FRBs. And we have about 15 outrigger antennas. Here it is about a month and a half ago. This is the east-west arm. And throughout the rest of the year, we're going to populate the rest of the T. So we're going to fill in the north-south arm and increase our sensitivity by about a factor of 2 in the blind search. Oh, thanks. Okay, so with 5-meter dishes at L-band, we have about 10 square degrees field of view. Of course, there are a lot of galaxies in 10 square degrees. And so we can get roughly arc-second precision with our offline interferometric localization. Here you can see in the top left, the PSF using the full array. Here's a dirty image for one of our FRBs. The bottom left shows a cleaned image. And in the bottom right shows an example of how we actually verify the precision and the accuracy of our localizations. We use VLBI sources, NVSS sources, and then single pulses from bright pulsars. Okay, so in the first year of commissioning in 2022, we found 30 FRBs localized to arc-second precision. So we more than doubled the total sample of localized fast radio bursts in our first year. Here you can see little snapshots of images from, I think, I-band pan stars. And they're organized from lowest extragalactic dispersion measure in the top left to highest extragalactic DM.
If you squint, you'll see the top left has a negative extragalactic DM, and I'll talk about that in a second. And again, this is operating in sort of half sensitivity commissioning mode. Some of you know this, but we've begun naming our FRBs. This is not just to be cute. It's actually really helpful to just have a name so that you can be like, why does Ishita not have a host? Why is Mifanshan so scattered and so on? Rather than trying to remember a whole bunch of telephone numbers. This works in the regime of like 5 to 100 FRBs. I don't think CHIME should do it, but it's useful for us for now. Here's Zach, Whitney. Wilhelm is interesting. So one of our summer undergraduate researchers, Ray Squatche, called this Wilhelm after the Wilhelm scream. It was like 300 sigma when we detected it. You can see it saturates at the top. And interestingly enough, despite having a kind of moderate extragalactic DM, there's no host, at least in pan-stars. Mark, so I alluded to this one before. This one was interesting because the detected DM was actually lower than what both NE2001 and YMW suggested the ISM contribution should be. So NE2001 thought in this direction, the ISM should give, I think, 130 units of DM. YMW said 190. And we measured this thing with a total dispersion measure of 110. So we thought, is it galactic? Is it extragalactic? But sure enough, it sits right on top of this face-on spiral galaxy at 50 megaparsecs. And the probability of that happening by chance is very, very low, something like 10 to the minus 4. So we're pretty certain it's extragalactic, and this allows you to constrain the DM coming from the Milky Way. So X mentioned this. I think I probably updated my prior closer to 0 than X has. I think there's no reason why the halo DM couldn't be 20 or 25 or 15 or something like that. But anyway, this low DM source allows us to constrain the baryonic material in the Milky Way's halo. We've also found 2 FRBs that come from massive galaxy clusters. So here I'm showing a light cone, and the heat map sort of shows the projected galaxy count. And so for this particular FRB, I was expecting it to be at redshift 0.6 or something. Its extragalactic DM was 600. But it clearly lives in this massive overdensity at redshift 0.1. Same is true for another FRB. This one is called Jackie. And sure enough, when you cross-match against a galaxy cluster catalog, you find that both of them reside in galaxy clusters and well-known clusters, Able clusters. This is Able 2310. Because it's relatively nearby and it's massive, there's archival X-ray and SC data. It's in the Planck SC2 cluster catalog. And so you can do fun things by combining those archival data with the FRB dispersion and rotation measures and learn something about the intercluster medium. This source, the galaxy cluster FRB Jackie, is interesting because it lives in a massive elliptical with almost no star formation. And this is work done by Kriti Sharma, who's here, as well as Caltech graduate student Jean. If you haven't met Kriti yet, you should definitely talk to her. She's expert in a lot of the things that are relevant to this meeting, namely optical IR, host galaxy follow-up. Okay, so by chance, DSA and CHIME are at very similar longitudes. And they're both transit instruments. So CHIME has no moving parts, of course, and it has maybe a couple degrees in the east-west direction and can see almost the whole north-south sky. The DSA 110 is also a transit instrument. We can move around in elevation, but not azimuthally. And so we're always co-pointing, which is sort of a happy accident. By the way, I made this slide on the plane yesterday when we were just south of Las Vegas. I couldn't connect to the Wi-Fi. So anyway, I can show this cartoon or this image I made, I think for my PhD thesis many, many years ago. This is roughly what the geometry looks like. So we have 10 square degrees. It's almost perfectly fits inside of CHIME's beam. So everything we see, CHIME also sees in principle, but the converse is not true. And remarkably, it seems like ultra wideband FRBs are fairly common. We find that about a quarter or a third of our detections are co-detected by CHIME despite the different frequency bands. So this means we see emission for a reasonable number of FRBs all the way from 400 megahertz up to 1500 megahertz. The science hasn't really been fleshed out fully. We have an agreement with CHIME, and I think it's going to produce some really interesting stuff. It's going to be led by Jacob Faber, who's also attending this meeting. We have an exciting polarization paper coming out, led by graduate student Miles Sherman. So this will be a couple dozen FRBs for which we preserved or detected polarization emission. So this paper will have things like PA behavior across the pulse. I'm hesitant to say swings because as you can see here on this trace on the Poincare sphere, it's not a simple swing like you see in some pulsars, as well as Faraday rotation measures and analysis of magnetic field, local magnetic fields, kind of like Alexander Manning's work. Casey and Kriti are working on a sort of gold sample host paper. I won't say too much about this, but I'm sure they're happy to chat about it at this meeting. This will be coming out relatively soon. It's got 11 FRBs in it and their host galaxies. And then finally, again, I won't say a ton about this, but we have 3 sources, maybe 2 or 3 candidates that we think are beyond Redshift 1. So that's also exciting. Okay, so to summarize, we find about 1 FRB per week when we're actually on sky and observing. We have just under 40 FRB localizations at this point. Early science includes a number of applications, the ICM, the Milky Way's CGM, intervening CGM science, which I didn't talk about today. And then the sort of progenitor science, the bread and butter of the FRB community, host galaxies, propagation effects, polarization, all these sorts of things. Co-detections with CHIME FRB are common. I think that's really exciting. I think we'll learn a whole bunch about propagation and the emission mechanism. I think we spent a lot of time thinking about repeaters. We spent a disproportionate amount of time thinking about the frequency spectra of repeaters, which are clearly more narrow band. They've got more interesting stuff going on in their dynamic spectra. Non-repeaters are kind of boring. They're fairly narrow. They're ultra wide band in many cases. And if you look at the distribution of bandedness for CHIME non-repeaters, a lot of them are wider than 350 megahertz. So that's interesting for DSA 2000 and for CHORD, which are both ultra wideband instruments. And then finally, we expect about a factor of 2 in sensitivity, maybe factor of 3 in detection rate from increasing the number of antennas on the core of the DSA 110. And we'll be rolling that out towards the end of the summer. Thanks.
Thanks, Liam. We have time for 2 questions. I guess we'll start with Xavier first.
Thanks, Liam. Question on the ultra wide detections. Have you had a chance to think about whether there's any conflict with the inferences on scattering that have been published to date?
This is one of the questions that we hope to answer when we do a deep dive into this stuff. Most of the science that's been done on this topic came from a kind of impromptu meeting when Vicky and Paul happened to be at Caltech, and we were comparing dynamic spectra. And there were cases where an FRB would be a little bit scattered at DSA frequencies and then extraordinarily scattered at the bottom of the CHIME band. So I think there's going to be some really cool stuff to do.
I'll take your bait. Sure, repeaters, narrow band, often nearby. These one-offs, if they're broadband and so far away, the emission mechanism implications of making something so bright over such a large range of bandwidths is amazing. You should really go after that.
Yeah, it's a good point. It puts more pressure on the energetics.
I think that's all the time we have for questions. We'll move to the next speaker, who will be joining us remotely, Tiaan Bezuidenhout, who will be telling us about MeerTRAP. You're free to start anytime, Tiaan.
Okay, I'm going to shut down my video because my connection is iffy. Sure. Hi everyone, my name is Tiaan Bezuidenhout. I'm a postdoc at Northwestern University in South Africa, and I'm also a member of the MeerTRAP project, which is carrying out a real-time search for radio transients with MeerKAT. So I want to show you some of our results, especially our transient or our localization efforts. But first, I'll give a quick recap of what we are doing. So we have a commensal survey with the 8 MeerKAT large survey projects. So we have a custom backend that is continually taking the voltages from the antennas and doing a real-time single pulse search. Candidates are vetted by a machine learning algorithm as well as by eye. You should know also that we operate in 2 different observing modes at the same time. In the first place, we use all 64 dishes to form one big incoherent beam of 1.27 square degrees, which has a sensitivity comparable to the Muriang telescope. And then we also use only the 40 core dishes to create up to 768 each of which is seconds, and which has a sensitivity comparable to the Greenbank telescope. And we tile those throughout. Hello, I am back. I don't know how far I got into that before I lost you. Okay, so we operate in 2 distinct observing modes. Can you hear me?
Yes, we can hear you. Yeah.
Okay, okay, I'm gonna continue. So we operate in 2 distinct observing modes at the same time. We form an incoherent beam with using all 64 dishes added together incoherently, which gives you a sensitivity around the same as the Muriang telescope and field of view of 1.27 square degrees. And then we also use only the 40 core dishes to create up to 768 tidal ray beams, each of which is about 45 arcseconds wide, as the sensitivity comparable to the Greenbank telescope. So we tell that those throughout the incoherent beam to create a total field of view of 0.2 to 0.5 square degrees, depending on how you arrange the beams. And then more recently, we have also instituted a transient buffer system, whereby a trigger of the transient buffer results in 300 milliseconds worth of voltage data being stored that we can then use to rebeamform and perform some of the pulses. So that brings me to the juicy stuff, which is some results and numbers. We've been operating for 3.5 years now, continuously, in which time we found 82 galactic transients, 39 fast radio bursts, and of those FRBs, 12 have been in the incoherent beam, 20 in the coherent beam alone, and 7 in both. Also 26 of we've seen in the MeerTRAP L band, and 13 was seen with the UHF receiver. Then the transient buffer has been operational since around July of last year, although it's had its fair share of teething problems since then. So of the 7 imaging localizations that we've managed so far, 3 have come from transient buffer trigger events. So I'll walk you through some of our major FRB discoveries so far. The first 2 FRBs that we saw were these 2 FRBs that we saw in the incoherent beam alone, so they weren't seen in any coherent beams. And in that case, the best that we could do for localization was to model the beam response and exclude all positions where the FRB would have been detected in a coherent beam. So that's not super productive, but that's the best kind of first order localization that we get. Then the second one was an FRB that we got in one coherent beam. So again, we could model the beam response and thereby constrain the FRB to within the cyan contour, which is about a degree across. This was a bit more fruitful. We did a path analysis of the field, and we were able to establish a 92% confidence the host association with this galaxy at z equals 0.05. We also got a spectrum with the Goodman spectrograph on the SOAR telescope, from which we got estimates for the stellar mass and the star formation rates, both of which are in line with the host galaxies of FRBs. Next, we got some FRBs that were also only detected in one coherent beam. Unfortunately, these weren't super high signal to noise FRBs, so we were only able to constrain them to quite large regions. But we did do a path analysis again. So each of the sources circled by the green is a possible host galaxy for each of these, but we couldn't make any associations with any real confidence. Our next FRB was seen in two coherent beams and incoherent beam. So that allowed us to use a custom algorithm that I have helped develop called CCAT to localize the source to within this region of about 1.5 by 9 arc seconds. And this was overlaid on an optical image. There are two possible faint associations there, but we are still working on follow-up on this with the fast and fortunate FRB follow-up or to the full collaboration, which you'll hear about a bit more later. That brings us to our first FRB that we were able to localize with imaging. This one was detected during Thundercate's observation of the low mass binary GX339. Fortunately, that's an imaging survey, so they had some imaging data. Unfortunately, it was only with a minimum integration of 8 seconds. But this FRB was bright enough that we were still able to see it in an 8-second image. That's on the left there. And then also on the right, if you integrate over the whole 3.6 hours observation, we saw that there's a persistent source nearby to the FRB as well. So we overlay these localizations on a DECAPS optical image. The FRB in green there is about 0.2 arc seconds away from this G or K type star. But the DM contribution along that line of sight is far too little to explain the DM that we saw, so we conclude that's a chance coincidence. But the persistent emission we were able to associate with this star-forming spiral galaxy at Z equals 0.066, and we got again a spectrum of that with stellar mass and star formation rate estimates. The next FRB that we saw was not discovered during our usual concurrent observations. It was during an open time proposal that we put in to look at some well-localized ASKAP FRBs to look for persistent emission. And for this one, we had 2-second integrations. So we were able to use difference imaging to localize it to about half an arc second. We got a spectrograph, a spectrum with a Goodman spectrograph for the host galaxy, for which we saw that it has a low-ish stellar mass and a very low star formation rate, only about 0.03 solar masses per year. Then despite a couple of hours that we spent on follow-up with both MeerTRAP and MeerTRAP, we didn't see any persistent emission, nor did we see any repeat pulses, which is interesting because if you look at the dynamic spectrum in the middle there, it has the spectral bifurcation and the wide pulse width that you would expect for a repeater. So that's slowed down, and that might explain why there's why the persistent emission has faded away. Also interesting is that this FRB is a Macquart relation outlier. On the right-hand plot, it's shown by the yellow star. So this is an FRB that we definitely encourage some follow-up on as well. The next FRB was another one that we localized in an 8-second image, this time from Mongoose. We saw it in the incoherent beam as well as 7 coherent beams. We follow up with Gemini, show that there's a possible host galaxy, very faint, only 23.8 magnitude in there. So yeah, we're still working on that, expect to see more. And then the next FRB was a very, very bright one. We saw it with a signal to noise of 193 in the incoherent beam, as well as in 600 coherent beams simultaneously, so super bright. And in the deep field image on the bottom right, you can see that there's a hint of a persistent source there. So yeah, we're still working on this one. And then finally, that brings us to our first transient buffer localizations. These were 2 FRBs that we saw, one in the UHF band and one in the L band. And by overlaying the locations of these on a decam archival image, there are very possible host associations in that field. Yeah, more coming on that. And finally, the last FRB that we saw, the most recent one, we found in January of this year. We saw it in the incoherent beam and 1 coherent beam in the L band. The beamformed localization on the left gave us this annular localization region, with the white being the coherent beam location. And then the yellow cross is the localization given by the transient buffer imaging. So these 2 methods correspond well. Yeah, to summarize, we have found 39 phosphoradioids bursts so far, which amounts to about 1 discovery per month. 7 of these we've been able to localize using imaging, and another few we've got decent localizations with beamforming. So that works out to about 1/4 of our sample being well enough localized for potential host association. Then the transient buffer is now up and running finally, and that should dramatically improve our.
That was unfortunate that we lost Tiaan at the end of his talk. We'll see if he comes back online to answer any questions.
Hello, I am back. I think I might be in time to field some questions.
Yeah, sure, Tiaan. I think.
Thanks. Yeah, sorry for the bad connection. You know how it goes. It was perfect all day, and then suddenly.
No worries, these things happen. We're running a bit over schedule, but we have time for one question. Sure, Liam has a question for you, Tiaan.
So the FRB that you mentioned that had an enormous signal to noise, did you say that was discovered in the MeerTRAP deep field? Like, do you have that mapped out to microjansky RMS and continuum?
Maybe I can quickly answer that. No, it's not in the MeerTRAP deep field, as in the DEEP field. It's just what he meant was there is an image of the field we could make that was the entire observation we were commensal with.
Gotcha. Thanks.
Okay, let's thank Tiaan again. And our next speaker is someone I've never heard of before, Kyoshi Masui from MIT, talking about an instrument I haven't heard about, CHIME FRB, and its Outriggers experiment.
All righty. Thank you. So what? Yeah. Oh, yeah, I didn't redo my notes, so they're all wrong anyway. Good. Okay. Except now I can't see my slides. I can only see, well. Right. Okay. All right. So, okay, I'm going to tell you about the CHIME FRB Outriggers program. Perfect. Thank you so much. Yes, so let's jump right into it. So we all know CHIME's strength, right? Which is that we can we see more FRBs than every other instrument. And then CHIME's weakness is that we only localize those FRBs to about an arc minute. So our diffraction limit is about 15 arc minutes. Through heroic work by Daniele, we get that down to an arc minute through these baseband localizations through the transient, what other groups have been calling the transient buffer, which we call the baseband buffer, you know, all similar systems. And with an arc minute just isn't good enough except for the lowest DM nearest by sources. So if we want to unambiguously localize all of our FRBs, we're going to have to do much, much better. And in fact, there's two levels at which you could do better, right? So you could do something, laser pointer, except you can't see it, okay. You can do something like on the left with traditional interferometry and get something like arc second localizations. And that will, in most, almost all cases, be good enough to identify the host galaxy. And does give you information about the, for nearby sources, gives you information about where in the galaxy it is, sort of like centroid offsets and maybe identify spiral arms. But if you get that really exquisite VLBI information at the milliarc second scale that can only be given by VLBI, then you can do these ultra detailed studies and say, oh, you know, this source is not only associated with this galaxy, but it's associated with a star forming region. Actually, it's not quite associated with the star forming region at 60 parsecs off. That's the challenge for the magnetar hypothesis. La-di-da-di-da. All this extra rich information you get by really having these ultra precise localizations. And so we'd like the second over the first, right? If you have the choice. With that, let me introduce the CHIME FRB VLBI Outriggers program. And so this is just a project to construct mini versions of CHIME all over North America that co-observe with CHIME and do VLBI on CHIME FRB sources. So each one of these outriggers is about 1/8 of the CHIME collecting area, except for the short baseline, which is 1/16. We have to do some sort of clever things, especially in the east. We have to roll that cylinder on the side because CHIME looks straight up. What is straight up in BC is not the same as what's straight up in West Virginia. And so you have to roll on the side. But other than that, optically, they're very, very similar to CHIME. Very similar in analog and digital systems, but just smaller in scale. So the cylinders themselves are the same width. It's just we have less length, less numbers of cylinders. Okay, and so the goal of this project is to localize most CHIME detected FRBs, which will be ultimately thousands, to better than 50 milliarc second precision. Okay, but how do we do this? So this is sort of a new way of doing VLBI, right? We don't know where or when the VLBI target is, right? So VLBI is intrinsically or has not intrinsically actually, but it has traditionally been a very targeted method, right? It's zooming in on a source. You have to know where that source is. In most astronomy, you know when that source is. It's usually always, not in FRBs. And you have to so you know, FRB science over a wide field of view does not lend itself well to how VLBI has been done in the past. And so we have to sort of invent techniques to make this work. So what are some reasons that this is like really hard? One is the data rate, right? So there's a fundamental scaling in the data rate, which is that that the amount of data you have to produce, collect for phase preserving. If you want to preserve phase, which is the data, the baseband data that you need to do VLBI, there's a fundamental scaling that says that the amount of data you need to collect scales as the field of view times the collecting area times the bandwidth. Okay, and that is arguably the number that CHIME was designed to maximize. It was designed to have the biggest field of view, the largest collecting area, and the largest bandwidth. And so we've designed an instrument that makes this maximally hard, lets us discover lots and lots of FRBs, but makes it kind of impossible to collect the data that you would need for VLBI. So that data rate is 100 times higher than an EHT system station, which is the next biggest VLBI recorder, highest bandwidth VLBI recorder that exists. Similarly, you've got calibration problems you have to do. So in VLBI, you have to calibrate things like the clock, the ionosphere, a bunch of other things. And we don't know where on the sky to calibrate. We don't know when to calibrate, right? And so you just kind of need like these always ready calibration solutions. So I'll run through how we're working on solving a couple of these problems. So the data recording system is a problem that we actually solved before we thought about having to do VLBI. And so this is this baseband ring buffer, what it was called in the last talk, the transient ring buffer, right? So the way CHIME works is, a cartoon of how CHIME works is you have the telescope at the top. It produces the measurements of the raw measurements of the electric field, these phase preserving measurements from all the antennas in the array. And that goes into a correlator or a beamformer that sort of steers your telescope, and that's the data product that you use to search for FRBs, right? But that phase preserving data that comes at the top, that's what you need, and it's way too voluminous to ever collect. So we put that in a 40-second all-memory ring buffer, and it's constantly buffering. And then we read that out only on trigger of fast radio bursts. And then for the Outriggers, you can just duplicate that same system on the Outrigger. You don't need the beamformer, right? You don't have to search for FRBs on the Outrigger. You only need the phase preserving data. And so you get this sort of the side, a system that looks in cartoon form like this to collect this data. So in this way, we are collecting that data that's 100 times the EHT data rate, but we only need to collect it when we've discovered an FRB, right? Because that data, we only ever write it to disk. For most of the time, it just lives in this 40-second ring buffer. We write it to disk only when we discover an FRB. We only write a few hundred milliseconds of data for every FRB a few times a day, which is totally manageable. Okay. So then at our band, there's our band and our bandwidth. Our band presents a couple problems. Our bandwidth solves a couple problems, right? So this is a very, very sparse VLBI array, right? So we saw those dirty beams that Franz showed from the EVN, and they looked awful, right? They were very multimodal, and they had lobes all over the place, and so you don't get that really makes for much messier localizations, and there they have sort of of order 5 to 10 VLBI stations, meaning they've got order dozens of baselines pairwise. Here we only have 4 stations. And in fact, it's way worse than that because we don't use the inter-outrigger baselines. They're not sensitive enough. We only use the baselines that involve the CHIME core itself. So we only actually have 3 baselines on which to localize this FRB. So, in traditional interferometry, you'd say, okay, I've measured 3 Fourier modes in the sky, and I have to make an image out of 3 Fourier modes. How am I going to do that? So that's one reason that you might think we're crazy for being able to do this. Another reason you might think that this system is designed to not, the design of the system couldn't possibly work is that we're operating at much lower frequencies than almost every other telescope. So the ionosphere is just going to hit us way worse than any other instrument. And my claim is that our octave of bandwidth will help us solve both these problems. So how does that work? So you should not think of this as an imaging experiment. The dirty beam is kind of the wrong way to think of it, because fundamentally you only need to triangulate the location of the FRB, right? You only need to measure sort of 2 delays to really localize the FRB. There's only 2 numbers you don't know, the RA and the DEC. Okay, so So if you stay in Fourier space and say, what is it that I measure? Well, I measure a visibility. The visibility has a phase, and that phase is proportional to the delay between my two stations, right? But critically, that phase is different at every frequency. And if you have a wide enough bandwidth with one baseline, at a single frequency, each baseline only measures a single Fourier mode of the sky, but I have thousands of frequencies. I've got a whole octave of bandwidth. And so since I have my full frequency coverage, if I can measure this one number, this tau AB, the geometric delay between the two sites, to well enough to localize, even if I have very sparse Fourier information in the sky, because fundamentally there are only two missing numbers, the RA and the DEC. Similarly, the ionosphere is really hard at our frequencies, but it actually has because that delay is dispersive, right? That also causes delays between our stations, but because that delay is dispersive, it looks very different as a function of frequency. And so if you can, in the phase of the visibility, if you can see the difference between the linear frequency dependence of the geometric delay and the 1/, frequency dependence of the dispersive delays from the ionosphere, you should be able to separate these and have all the information you need, given enough bandwidth and enough signal noise. Similarly, we still need to calibrate, right? And the abundance of calibrators for our baselines in our band is very poorly known. So LOFAR has done some work, but it's done at shorter baselines than us. There's lots of work that's been done at much longer baselines, but at higher frequency. So in our actual space of baseline and bandwidth, we actually don't know the abundance of VLBI calibrators, but what we do know is that pulsars exist. And so that's like the minimal set of calibrators that we know have to work. These pulsars are guaranteed to be point sources. They're guaranteed to be visible by CHIME. And so there's sort of heroic work being done to make sure that we have this minimal set of calibrators that are guaranteed to work, even if we don't have a good handle on our more traditional continuum calibrators in our band. Okay, so just to prove that a lot of these sort of techniques work, there's been a campaign to prototype a lot of these technologies that has been pushed ahead by the people on this slide, and that's using these systems at the Algonquin Radio Observatory and prototypes at GBO to test these things. I won't go into this in detail except to say that they have achieved the first ever VLBI localization of a non-repeating, or at least at the time of detection, a so far non-repeating fast radio burst. And so that's kind of a milestone for us that we've proven that many of these technologies work, and that we can actually do this. Okay, so what's the status of all this? These telescopes do exist. They're still on the ground, right? So this is a few month old, or maybe even almost a year old image of our KKO outrigger and BC. Just last week, this is an earlier image of Mark Carson from UBC, and last week this is an image of Tom Landecker and Nico, who's in the crowd, adding some weather station instrumentation to it. So site work continues, but overall this is sort of like a working telescope for our shortest baseline in BC. Similarly, the telescope in Greenbank also works. And also last week, there was a bunch of people on site adding all the digital instrumentation. So there's a very dignified picture of some of our site team, including at least 2 members of the scientific organizing committee. And this was taken on, I think, on Wednesday. So this is a working telescope now, or not yet commissioned, but has all the hardware is there on site. Less impressive is Hat Creek, which this is a year-old image, but it doesn't look too much different than it is now. Yeah, I see Vicky's like rubbing her face because of the permitting issues that we're facing here. But we're hoping that those are all sorted out and that the steel will go up very quickly over the summer and instrumentation to follow shortly after. Okay, so and to show that we are also doing, actual analysis, right? So this is just commissioning data. There's nothing. This is just sort of nothing hugely insightful, except for the fact that we are using the sky. Those are the bigger, bolder dots to measure sort of clock offsets between the two clocks at KKO and at CHIME. And those measurements agree with our internal measurements of what we think the clock is doing to very high precision. So that's not, I don't think, this is just to show we are doing VLBI between these sites, and we are measuring things, and those things are understood. And this is effort by a heroic team of people that are analyzing this data to bring this all together. Okay, so that's all my time and all everything I wanted to say. So it's just that Outriggers are going to augment CHIME's unprecedented discovery rate with a VLBI style 50 milliarc second localizations of all FRBs. We've had to invent a whole bunch of new technologies to do this: data recording, calibration, analysis techniques, just to enable this sort of synoptic transient VLBI technique. 2 out of these 3 Outriggers are now sort of in the commissioning phases. Third will be constructed over the summer, hopefully, and you should expect great things from us soonish. Thank you.
So we're running a bit over time, so I think Kiyo can answer questions in person after his talk, and we'll move on to our next speaker, who is Tarraneh Eftekhari, coming from Northwestern University and talking about the F4 collaboration.
Okay, great. Oh, we good? Okay. Okay, so today I'm excited to talk about some of the work that we've been doing within the Fast and Fortunate for FRB follow-up, or F4 collaboration. This will be kind of a grab bag of some of the most recent projects that we've been working on. And then I'll spend a few minutes at the end of the talk talking about some follow-up infrastructure that we've been developing. And this is really designed to optimize follow-up in the era of many localized events. And I just want to highlight that the work that I'll be discussing is really a huge team effort. So F4 members span multiple institutions and countries. This is our team today. So in addition to our fearless leaders, including X, who we heard from this morning, we have a small number of postdocs and also quite a few students who are actively leading projects. And some of those students are here at the workshop this week. So I will be discussing some of the work that they're doing, but I do encourage you to seek them out and talk to them about their work. Okay, so the way that F4 operates is that we partner with a number of FRB discovery experiments to conduct follow-up of well-localized events. So typically an FRB is detected to within a few arcsecond precision, and then working together, we conduct a whole host of follow-up using both ground and space-based instruments. And this is not only to study the host galaxy and obtain a redshift, but also to search for multi-wavelength counterparts, as I'll discuss. And what this means is that we're really doing science across the entire electromagnetic spectrum, from radio to X-ray wavelengths. From a host galaxy perspective, this allows you to study star formation on different timescales, for example, or to probe star formation in particularly dusty environments. And then, of course, there's really this open question when it comes to multi-wavelength counterparts, right? What are the expectations in terms of both prompt and longer-lived emission? And so this is an area that we're also interested in exploring. And so for the next several slides, I'll take you on kind of a whirlwind tour of some of the various projects that we're working on. Okay, so starting at long wavelengths, radio observations of FRB hosts have thus far led to the discovery of 2 persistent radio sources, as we all know. And then in at least a few cases, there's also radio emission that's detected from the galaxy itself that's associated with star formation. So one such example is FRB 2020-1124A. This is a hyperactive repeating FRB, and it's also the first repeating FRB that is associated with radio emission that is attributed to star formation in its host galaxy. So Vic Dong, who is here at the conference, is leading a high-resolution radio study of this host galaxy. And the idea is we really want to understand the local environment around the FRB. And so in this case, we are finding that the FRB is in a particularly dust-obscured environment. And so we ultimately want to understand what that implies about its progenitor and how that might connect back to its hyperactivity. Okay, so moving into the millimeter regime, there's been some recent work by Jay Chidity working on using ALMA to probe the molecular gas content in FRB hosts. And what we're finding from this sort of initial sample of millimeter observations is that FRB hosts seem to have somewhat higher gas fractions when compared to local galaxies. And so this is giving us some insight into the star formation mechanism in these galaxies. So for instance, you expect younger or more massive stars to exist where there's a lot more molecular gas. And so this at face value is really pointing to massive star progenitors. But of course, we want to expand this type of analysis to a much larger sample of hosts with millimeter observations. And I'll just mention that this paper just appeared on the archive last week, so I do encourage everyone to check it out. Okay, so moving on into the optical regime, Alexa Gordon, who is also here at the conference this week, recently released the largest compilation of FRB host properties and star formation histories. And what we see in the top left panel is that FRB hosts really do seem to trace the star forming main sequence of galaxies. So they do exhibit quite a range of star formation rates and stellar masses. And there is some evidence that perhaps the hosts of repeating FRBs extend to lower masses and luminosities when compared to non-repeating events. In terms of the star formation histories, we find that most FRB hosts peak in their star formation in the last gigayear or so. And so taken all together, this really supports a picture in which FRBs come from magnetars that are formed through core collapse supernovae. However, we do see a few quiescent hosts, and this would point to more delayed progenitor channels for those sources. And you can imagine that as we move into the regime of having many hundreds of well-localized FRBs with hosts, it will start to become more clear whether repeating versus non-repeating events sort of preferentially live in unique environments. Okay, there's also been, so that's sort of more on the host galaxy side of things, but we can also do really nice astrophysics and cosmology work, as we heard this morning. And this is work that's led by Sunil Simha. And here he's using spectroscopic foreground mapping of galaxies to map the DM halo and DM host contributions of FRBs. And the idea here is that you can take FRBs where the DM cosmic value is larger than average, and you can obtain spectra of all of the field galaxies in order to pinpoint how much of that excess DM comes from the host galaxy or from intervening galaxy halos. And so in Sunil's latest work, what he shows is that for the sample of 4 FRBs with excess DM, one can attribute the excess DM in about half the cases to foreground matter, and in the other cases to excess host contributions. And so again, this is an example where once we have many localized events and with foreground mapping that's done, we can really start to place some nice constraints on the distribution of baryonic matter. And I should say Sunil is attending remotely and he is on the Slack, so definitely ping him with any questions. Okay, so that is kind of on the host galaxy and cosmology / astrophysics side of things. But as I said, we're also interested in looking for multi-wavelength counterparts. And this is one example in the optical regime. So this is work led by Charlie Kilpatrick. Here he's using the Alopeki high-speed imaging camera on Gemini to look for fast optical bursts to FRBs. And so in this particular case, he is observing the repeating FRB 180916. And the idea here is that given the sort of known period activity of the source, and we can take into account when the source will transit at CHIME in order to perform coordinated optical observations and really try to detect an optical counterpart at the same time as the burst. And so that's shown in the top figure up there. The red points correspond to the background count rate coming out of the detector. And that vertical line is the time of the FRB itself. So these observations have already led to the deepest limits on optical counterparts on timescales comparable to the FRB emission. So we're talking about 10 milliseconds here. And we are in the process of expanding this type of analysis to a larger sample of repeating FRBs. So we can really kind of push down on this parameter space when it comes to FRB models that do predict optical emission. And we'll hear more about searches for optical bursts from Daichi later today. Okay, and then finally, we have been doing some work in the X-ray regime to search for AGN in FRB host galaxies. So when we look at the latest compilation of BPT results for FRB hosts, we do find that a subset of hosts show evidence for AGN and liner emission. And in the case of the liner galaxies, we're especially interested in understanding what is the source of ionization in those galaxies. So for example, is it AGN emission or could it be a population of evolved low mass stars? And that's sort of what we would expect if, for instance, FRBs are coming from delayed channels. And so we've been conducting a pilot Chandra program and working on compiling all existing X-ray observations of FRBs. And ultimately, again, we're really interested in answering this question of, do FRBs live in host galaxies that harbor AGN at an elevated rate? And then similarly, separate from searching for AGN, we can also search for X-ray counterparts. So this is especially interesting in the context of ultraluminous X-ray sources. So these were proposed as possible FRB progenitors in light of the observed periodicity from a few events. But based on what we're finding from our initial observations, is that most X-ray observations for FRBs are really not probing the luminosities of ULX counterparts. And so this is really just kind of highlighting that if we're interested in detecting X-ray counterparts from FRBs, our efforts are really best spent going after the most nearby events. Okay, so that is a very quick whirlwind of just some of the projects that F4 is doing. But the point that I do want to emphasize is that it is important to really build up this kind of multi-wavelength picture of FRB host galaxies if we want to make progress in understanding their progenitors. And especially as we move into this regime of having, hundreds of well-localized events, thousands as we're hearing, this really necessitates sort of optimizing our follow-up efforts and our resources. So this has been the motivation behind the F4PZ Target and Observation Management Tool. Still not sure how to pronounce it. So this is basically a dashboard-based user interface, and it is built off of the existing infrastructure that's used for the young supernova experiments. And so this interface basically keeps track of all of your FRBs, queries archival data. For instance, it'll pull images of the host galaxy from optical surveys. And then importantly, it also manages the allocation and scheduling of your observing resources. And so you can imagine when we're really, we're talking about hundreds of FRBs, a tool like this will be extremely helpful. And we already have a few examples of moving into this sort of large N era within the F4 collaboration. So this is a VLT large program in collaboration with the CRAFT team designed to obtain imaging and spectroscopy for 50 FRBs discovered by ASKAP. And the idea here is that we can build up a really nice homogeneous sample of FRB hosts to study, both their stellar populations and also their spatial offsets and see what that might imply about their progenitors. And then building on that, we recently submitted a Gemini large and long program with the CHIME team. So this program is designed to obtain redshifts for 200 FRB host galaxies. once CHIME Outriggers come online. And you can see that we'll be probing quite a wide range in galaxy types over a very broad redshift range. And we'll also be able to place some very high precision constraints on cosmology. So we're very excited for this, hoping it gets approved. So fingers crossed. And then the last thing I want to mention is that we are working on a host galaxy catalog for FRBs for the wider FRB community. For those who are familiar with the Open Supernova catalog, we envision it as being fairly similar to that. So this will be a repository where you can sort of easily sort or search through tables, look at images of the host galaxies, download data sets, and so on. And we certainly welcome any suggestions from the community. We really want this to be a tool that best benefits everyone. So please do let us know. And with that, I'll just say that, at F4, we are very excited to be moving into this new era of FRB science, where there will be tons of really interesting science to do. And so one of the things we're really interested in is making sure that we have the tools to kind of really maximize the scientific return. And from that, with that, I'll go ahead and end and take questions.
Thanks, Tarraneh. We have time for one question. Yes, Yuri?
That's very nice. Thanks so much for presenting that. So at the bits about the X-ray counterparts you mentioned, look, if they're ULX type, you can really only go after the nearby ones. But really, how is this different from for much of the other multi-frequency follow-up? And so my question is, in your dashboard, for example, is there how to put in the strategy? Should we optimize for nearby ones? Do you want to optimize for high Z ones for cosmology? What's the strategy?
Yeah, that's an excellent question. And my kind of initial thinking is that it'll certainly be wavelength dependent. I think for radio counterparts, there's a lot more leniency there in terms of expectations and sensitivity of radio instruments. For X-ray, clearly less so. So yeah, that's a very great point that should be built somehow into the observing strategy in the dashboard. And I think, maybe something for the discussion session, but also thinking about whether populations of FRBs from different experiments would be best served with different follow-up resources.
Great, let's thank Tarraneh again. And we have our last speaker of the session before lunch, Jeff Cooke from Swinburne University, talking about the Deeper, Wider, Faster program.
So two things you want to hear as a speaker is we're over time and lunch is next. But hopefully I'll keep you entertained until then, okay? So I'm going to tell you about this program that's been going on for 8 years now, surprisingly, called Deeper, Wider, Faster, and it's a proactive approach, not reactive. Like if an FRB happens, you don't react to it. It's actually, you're there ahead of time. I'll explain all about that. I am mostly interested in what FRBs are. That's my biggest interest. With progenitors, what are they? And it's really good to see some of these happening at high redshift, because that's a lot of my experiences at high redshift galaxies. So that'll be interesting to see how that pans out. Okay, so at the bottom there, you probably have read or not, but this is a deep wide field, fast cadence, radio through gamma ray, so all wavelengths and particle detectors, coordinate observations on the same fields at the same time, searching for fast transients. Okay, there's real-time data processing, transient identification, coordinated rapid response follow-up, conventional TOOs, intraday observation, and weeks later monitoring. That's a big mouthful of words. Okay, and I'll try to get through that as best I can to make some sense. Okay. So just what do I mean by fast transients? Because this does fast transients and FRB counterparts. And just really quickly, this is like millisecond to about a day timescale. That's fast in this context. In a radio, there are a lot of transients, as we know, kind of in the middle swath there, from FRBs to GRBs, et cetera. And in the X-ray, again, this is the timescale. So, fraction of a second to a couple of days. And there are a lot of transients there that need exploration. And most of these things have been followed up in a single wavelength band, unless you have some targeted source. But in the optical, things early on kind of look like this. Off to the right there are just conventional transients. And what is on fast. And that's mostly been limited by technological, capabilities. You got to process lots of data, and there's millions of objects in wide field images, et cetera. And we knew about gamma ray bursts and some galactic things like flare stars and et cetera that happen on fast timescales. Great. Well, the program, when we started, that was about it known. And then over the last about 8 years, a bunch of things are filling up this space as expected, because nature doesn't leave anything open. And so you see a whole bunch of things like fast luminous transients, kilonova, as we know now, et cetera. And there's still a lot of space to go. And this kind of yellowish, greenish region is sparsely populated, probed by anybody. And that is also, where fast radio burst counterparts could exist, but there are a whole bunch of other theorized and interesting things in that regime that we're trying to cover. So DWF kind of covers all of this region with a giant. Right, if it's going to be a coherent burst at an optical wavelength, that actually happens before the FRB. So no matter how fast you can trigger, you're not going to be on it. You've already missed it. If it comes at the same time, that could be seconds to minute before or so. And so you need to basically have some kind of simultaneous all wavelength ready for anything kind of situation to get the fastest transients that are really fast. And for things that might be minutes to an hour or so, if you're processing things fast, you can actually go after those with rapid response telescopes. It could be like SWIFT or with an 8-meter telescope on the ground or something, and you get some spectra, try to understand what they are. And then actually things like supernova shock breakouts, which are fast, but they're associated with a slow supernova, right? So you can just monitor that later. So you need kind of field monitoring as well. So all of that's encapsulated in this program. And I'm going to take you back to a golden era in 2014 when FRBs were just starting to be detected in real time. And as that happened, this program was devised to figure out what they are. That should be easy, right? Just get some optical on them or something, or some easy, right? So we developed a program, and this was years ago when my hair was not gray, where we were looking, and we put together DECCAM, which is a wide field optical image on a 4-meter telescope. We did fast, like 20-second, we still do 20-second continuous imaging. And we used SWIFT to get some high energy and wavelengths and park them along with to get radio. It all worked well, but turns out FRBs don't happen that often, and it's really hard to coordinate telescopes. And so this only happens like once or twice a year, and you just got to be lucky, basically, it turns out. Well, that grew over time, and gravitational wave detectors came online, and we actually found gravitational waves after that. And some other instruments here for follow-up were built on. People thought this was a really interesting concept. And now there is just a lot as part of this program. We have about 100 telescopes involved, over 200 collaborators, 40 institutions, 20 countries. Every continent has a telescope that we're using in space. So it's quite a large collaboration. But for any one given run, which again only happens like once or twice a year to coordinate this, we're only looking at a fraction of these because the Earth is round, so you can only have so many on the field at the same time. And so like 30 or so of these would be active. Okay, so this is the concept. And it's very successful. So just really quickly, we have kind of 4 general components. We have a fast, like a simultaneous thing. So this is aimed to get to be on sky before, during, and after anything happens. So we have deep observations. We'll coordinate 10 or 15 telescopes, as I mentioned, and it's from radio all the way to gamma ray. Then we have real-time data processing. A lot of satellites have onboard processing, but we're clustered a radio telescope. But the optical we found out was really a challenge. Here we are taking DECCAM data and trying to process it in a minute. That's a bit tricky, but we managed to get in a few minutes, which is good enough for fast things. And we keep doing this all night long, and we look for, and we have fancy machine learning software and this human visualization technology and stuff to help us out. In the program, we apply for a lot of time on and have collaborators with time on like Gemini and Keck and other, well, not Keck, but Gemini and BLT to do rapid response, like minutes later triggers, and then other telescopes like SALT and et cetera to do hours later. And of course, we have like compact array and high energy telescopes like SWIFT to trigger fast. And then the late time follow-up I talked to you about is just there's like a network of telescopes around the world that we use to monitor things as the Earth turns. Okay, so when it's happening, we all kind of in this control room here, mission control, we call it, and try to process stuff in real time during the processing. So we're trying to get all this information at once and integrate it, and to trigger telescopes and keep things to get on things as fast as we can. So a lot of fast transients over the time. To the left, there is a flare star, and to the right is some still mysterious fast transient that bursts a few times and goes away, and still don't know what that is. So there are some mysterious things out there. There's no way I can go through any of the things really in detail, so feel free to ask me later, but here's like a list of things, okay, that we've discovered and had some aspect to it, so we can talk about those later. But there's quite a range of interesting things, fast and slower and, very dynamic universe. And in one sense, we're classifying the fast transient sky for Rubin and other surveys in the future, because DECAM is very similar to, well, it's wide field and almost as deep. Okay, so yeah, and here's just some light curves. These are minute cadence points, so you can see how things change in minutes. And I think relevant to this conference, to the right, there are these are sub-minute optical detections. So these bursts last less than a minute, and they're seen in galaxies. So that's interesting. So we're going to try, hopefully we can really pursue those and see what those things are. Yeah, I'll get into the FRB counterparts quickly here. So, we all know that there could be more than one origin. There's kind of this prompt thing. People tend to look right when it happens, or a little before, or a little after. So there's that approach. But then there's this, I don't know if latent's the right word, but there's this thing where, it could have happened years ago, right? It could have been something, and then you got the magnetite thing, or years later. So we have to be open to all of that. So when we run this program, there's going to be like normal FRBs found, which are the normal high signal to noise, and then we have been pushing into trying to getting some low signal to noise FRBs, and since we have multi-wavelength data, we can kind of look into those. There's been a series of unfortunate events because we've had a few of these detected, and it seems that it's cloudy at the optical telescope, or the satellites in the south anomaly when the FRB happens. I mean, everything you think bad happens. You're thinking, how many telescopes do we have to get at once? Come on. But we do our best, and hopefully this will pay off soon. But I'll leave you with something that happened in September 2020. Of course, it was COVID, so we had to run all this from our houses, which was a challenge. But here were some of the telescopes that we coordinated simultaneously, from high energy to dark energy camera parks, etc. But because of COVID, their dark energy camera was not accessible. There was restrictions, so we used the KMT net, which is in Australia, which is a 1.6 meter, as a backup. Here's its field of view, 4 square degrees. That's great. The park's multi-beam is that big, so it kind of fits pretty well, especially if you offset it like that. The center beam, we set it on FRB 190711 because it's a repeater, so we knew there's a known repeater there, and then we're just looking in the field. And these are just some of the fields of view of the other things that were on the field, HXMT, X-ray, and Astrosat, UV, and etc. So during that run, we found not one, but 2 FRBs during the run. And here they are. And that's kind of interesting because, you've got 3 FRBs and a known repeater, all within like a degree on the sky, all with similar DMs. So that's already an interesting result. And so we're looking into that in more detail. And well, this is just coverage, the different telescopes that were on during the moments where that vertical line is the FRB. I'm just going to zip through this. We looked afterwards to see if they repeated, and there was no repeat. So just in the interest of time, I'll just mention that. But we looked back in time in this field to see what was there, and we saw, okay, there was a transient in the field like a year before that, and we said, great, here's the transient in this galaxy, and here it is in the beam where we found the high signal noise FRB, and we also saw a low signal noise FRB, which is in the same beam when it was pointing at the same area, and that little circle is where that galaxy is. We thought, oh, that's interesting. It's right in the middle. Cool. Then we got a spectrum of it. We got the host galaxy, and it looks, traditionally like a FRB host galaxy or something. So, okay, that sounds great. But then when you look at the redshift and we see the magnitude of the transient, it turns out it's a superluminous supernova. Now, those are very rare events, and that now we're looking at like a very low probability. And, are we raising the superluminous supernova thing again? I don't know. Okay, so it's interesting, but the fact that, here's that galaxy in our DECAM images. later that we took, and that's the position of where it is. And if you, I can't show you, but this is a barred spiral galaxy. It's got a really, scaling is bad, but it's got a clear bar going vertically and 2 arms. And then there's this kind of like streak going through that. Maybe it's interaction. I don't know, something happening. So it's just an interesting system, but it maybe a superluminous supernova happened and like a year later you have an FRB. I don't know, but it's just it's a curiosity. So I'll leave you with that and just tell you that DWF is ongoing. It's I think I'm biased a lot, but I think it's our best chance of finding a counterpart to an FRB. You got all wavelengths on it all the time, and we got a lot of coverage to search after that. So this is our this is the aim of the program. And in the era of localizations, I mean, what better than to have all wavelengths pointing at the same time? Thanks.
All right, thanks, Jeff. I imagine everyone's hungry, but we have time for a couple questions. Vicky?
So we've heard from different groups that some FRBs are found without any host galaxy so far. Those seem like really, puzzling sources that maybe could be like in the galaxy or something that might be associated with. So I'm wondering if any of the sources you've had good follow-up on are among those that don't have a host galaxy.
They aren't, and the 2 that I know of that don't have a host are potentially high redshift, so maybe it just needs deeper imaging, perhaps. But I will mention, talking about superluminous supernovae, since I work in that field, they're in low mass galaxies, usually low metallicity, and so they're going to be very dwarf galaxies, and are going to, you have to have really deep imaging if you're going to at any redshift. And so if FRBs have multiple populations, and if one of those populations is this, then you're going to have some subset of hosts that are just going to be really faint that you're going to have to go very deep to find. Exactly. Yeah.
Any other questions? Yuri?
That's all very interesting. I was a bit overwhelmed with some of the
okay,
info, so
yeah.
let me ask. So you found the superluminous supernova in master data from a year before one of the one-offs in your field of the repeater. Yeah, right?
Well, those both were found that same week, so yeah.
But the 2 one-offs, so you have 2
yes.
different one-offs.
I have 4 one-offs. So
okay, no, don't make it worse. Okay. You have 2 one-offs. Right? You had the 2 one-offs in the repeater field, right?
With different DMs.
Yes, different DMs, and one was signal to noise 10 and the other one was 100.
Yep.
So is the superluminous supernova FRB, is it the signal to noise 100 one or the 10 one? Oh, you don't know. Maybe you don't know.
So I would say that it was the low signal noise one because that DM was 110, which would be nice because this is redshift 0.08.
Yeah.
But as we've seen, the high signal noise one was a DM of like 600, but we've seen these cases where you're off in a poor relation. And so.
Yeah. Okay. Because I was thinking if the supernova remnant, the supernova was this recent, maybe there's still an absorption cutoff that you can see in the spectrum. And in a low signal to noise FRB, you wouldn't see it. So I was hoping it was the high. Maybe it is. Let's take a look.
Exactly. Okay. Good.
All right. One more question from Kiyo.
So I guess, that last result would have been, with the localization, it would have been, so much more cut and dry, right?
100%.
But you need an instrument that has order unity chance of seeing an FRB in a region that's covered by an optical field of view, in a day, basically, right? So I guess this is going to change a lot when like DSA 2000 and CHORD come online, where you've got a few square degrees, you can reliably get an FRB every day, right?
Yes, because if you look at the images that exist now, and probably the only ones that'll exist for decades, it's going to be dark energy camera, 3 square degrees.
Mhm.
Hypers prime camera, which we've used, 1.8 square degrees. And then of course, Rubin, but you're not really going to be able to use that necessarily for this. It's going to be doing its survey and stuff. So you got to find something in like a 2 square degree kind of window pretty fast, because you don't have a lot of telescope time's hard to come by and coordinating and stuff. So yeah, if you can find it in, I don't know, 100 hours or something, then you can do this.
Well, okay. 100 hours is even a lot, actually. I thought we were talking like, half a day or something.
Well,
but-
half a day would be, of course, because then you find more and you can start doing this work. But if you want to find like one or two, we run this about 35 hours a run, and it's like once or twice a year, so you add up the hours. Yeah.
I see a couple more questions.
Yeah.
Perhaps we should continue the discussion over lunch. I think we'll break for lunch now.